Hi everyone. Today we'll be having an example on hydraulic conductivity or permeability. The reference for this is the Fundamentals of Geotechnical Engineering by Das and Sivakugan. In this example, the soil considered is a fine sand and a test was conducted in the laboratory using a constant head laboratory permeability test. For this test, the following data are obtained or data are given. We have the length of the specimen. L is equal to 300 millimeter. The diameter of the specimen is 150. The head different H is 500 mm. The water collected in 5 minutes is equivalent to 350 cubic centimeter. For this test, we are asked to determine the following: the hydraulic conductivity of the soil in centimeter per seconds, the discharge velocity in centimeter per seconds also, and the seepage velocity with the same unit. The void ratio of the soil is also given to be 46. So in the constant head test, we are using a permeability test under a constant head difference. So let's try to draw the soil sample and the permeability apparatus. So we are given a permeability apparatus, let's say this one. I'm sorry. Okay, say this is the permeability apparatus. And then our soil sample is, say here, and here. So this is the fine sand. Having a length of 300 mm, or say this is 30 cm. Okay, normally prior to the fine sand, we put porous stone on top and at the bottom. Okay, so this is the porous stone. And the diameter of the specimen is 150, so there's no problem with that. And we have the head difference. So to get the head difference, what we normally do for this test is we allow water to flow through the permeability apparatus, through the permeability apparatus. Through a certain opening. Okay. All right, this is connected to a funnel, and this funnel will have a discharge here, or an overflow. We call it an overflow. Let me draw it better. So that when we allow water from the faucet to get in, water will flow here through our soil sample, but having a constant level only. There should be an overflow here so that the water will just have a constant level here. And once the water flows in our sample, we'll have to go out to our outflow, say here, and then water will be collected in a graduated cylinder. Okay, so here. And so the distance from our inflow to the outflow will be our head difference. And that would be our H. This is our H, which is equivalent to 500 millimeter or 50 cm. So here, the collected water is our Q, which is 350 cubic cm, cubic centimeter. Okay, so we need the hydraulic conductivity, K. And we have a formula for that. The hydraulic conductivity is given to be Q by L divided by A by H by T, wherein Q is the discharge or the total amount of water collected at a certain period of time. In our case, it is 5 minutes. Length, L is the length of the specimen, which is 30, and area is the area of our soil specimen. The diameter is given, so we can compute for the area. H is the head difference, and T is the time for the collection. So all data are given, so we can just plug in the values. Take note that we need the hydraulic conductivity in centimeter per second, so we have to convert some of the given values. Q is 350, that's already in cm. So this is cm cube. The length of the specimen is 30. This is in cm or centimeter all over. The area of the specimen, that is cylinder. Our permeability apparatus or permeameter is a cylinder. So the area would be, let's say, pi by 4 times D, or the diameter is 150 millimeter, and that would be equal to 15 cm square. And this is a square also. Then we have the head difference of 50 cm. So this is 50 cm. And the time required to collect the total amount of 350 is 5 minutes, or that is equivalent to times 60. Let's make it in seconds because we need the permeability in seconds. So 5 minutes is equivalent to 300 seconds. Okay. So the resulting unit would be centimeter per seconds. Calculating the permeability, we will get 3.96 raised to 10 negative 3 centimeter per seconds. So this is the answer for letter A. Normally for sand, the value is in the range of 10 to the negative 3 to the negative 2 up to negative 4. Then we have for letter B, we need to solve for the discharge velocity. The formula for the discharge velocity is equivalent to hydraulic conductivity by I, or the hydraulic gradient. And hydraulic gradient is equivalent to the head difference divided by the length of the specimen, or this is equal to K multiplied by H over L. So here we have 3.96 times 10 to the negative 3 cm per seconds multiplied by our H is 50 cm divided by L of the length of the specimen is 30. Okay. So V, or the discharge velocity, would be equal to 6.6 times 10 to the negative 3 centimeter per seconds. Okay. Then the seepage velocity is denoted as V sub S. And there is a derived relationship between the seepage velocity and the discharge velocity that can be found in the book. And that would be equal to V multiplied by 1 plus E divided by E. So this is a function of the void ratio, and the void ratio is given to be 0.46. So from here, we can solve for the seepage velocity, which is equivalent to 6.6 by 10 raised to negative 3 multiplied by 1 plus a void ratio of 0.46 all over 0.46. So the seepage velocity is equivalent to 20.95 raised to negative 3 centimeter per seconds. Okay, so that's how we calculate the permeability or hydraulic conductivity of a fine sand. Now let's have another example, this time considering a falling head permeability test. So again, a falling head permeability test is applicable for fine materials or for silt and clay soil. So in this example, the following values are given. The length of the specimen is equivalent to 38 centimeters. The area of the specimen is already given to be 19.4 centimeters square. The permeability is known, or the hydraulic conductivity value is 2.92 by 10 to the negative 3 centimeter per second. So what we are asked is the area of the standpipe. So this is the area of the standpipe, so that the head will drop from 64 cm to 30 cm or centimeters in a span of 8 minutes. So to give you the idea of the permeability test or falling head permeability test, this is a little different with the constant head test, because in the constant head test will have a constant head difference, but in the falling head test we have a different head difference at a certain time. So if you will look at the formula for the falling head test, the formula would be 2.303 A by L divided by capital A by T. This is log of, this is base 10, H sub 1 divided by H sub 2. So if you look at the formula, small a here is the area of the standpipe. Later we can see the standpipe. L is the length of the specimen. A is the area of the specimen, which is similar to the constant head test. H1 is the head at time t equals 0 at the start of the test, or at a certain time t, which is known dapat. And H sub 2 is the head drop or the head difference at a certain period of time. So in this case, it is 8 minutes. So let's look at the process for this falling head permeability test. So if we have, similarly, we have the permeameter or the permeability apparatus, say here, and we still have our soil sample here. See, here's our sample. And still have, oops, our porous stone here. We still have the outlet here, so that water will be collected in a graduated cylinder. And this time, we have a standpipe here, which is connected to our permeability apparatus. Let me just enlarge a little our standpipe. Oh, sorry. Okay. Let us just enlarge a little. Okay, this standpipe is connected to our faucet, of course, but we don't have a constant head this time, but this changes. Okay, when we start allowing water to flow here, and then water will get into our sample, it will pass through the porous stone, through our sample, and through the porous stone at the bottom, and it will go out to our outlet, to our graduated cylinder. The same L is the length of our soil sample, which is here is equivalent to 38 cm. The area of the specimen is 19.4, so this is our capital A, and then K is already given. Okay, if we look at our formula, let's check. The following are known already. We have the length of the specimen, we have the area of the specimen, time t is 8 minutes, or this is equivalent to how many seconds? This is t is equal to 8 minutes, that is 480 seconds. So this is already known. This is known, K. This is unknown, and H1 is known to be 64 and 64 centimeter, and this is 30 centimeter. So we can right away calculate A, but just to give you an idea on H1 and H2, or head difference 1 and head difference 2, that is when you start the test. Let's say time is equal to 0. We will allow water to flow, and when we start the test, we have to measure a certain height from our standpipe. By the way, this is the area of the standpipe, that is A. That's the unknown. So here we have from this point, let's say that's time equals 0, to our outlet, that is our H1, which is equivalent to 64 centimeter. Now, we have to stop water to flow from the faucet and allow the water to, from this height, from 64 cm, allow the water to flow down to a certain height within 8 minutes. So say after 8 minutes, from this point, water goes down to this level from in our standpipe. So from time equals 0 here to time equals 8 minutes, again, the faucet is already closed. We allow water to flow from this level to this level, and we get the height here, or the head difference, which is already given as 30 cm. So that's the difference between the difference of falling head permeability test to the constant head test. We don't allow water to continuously flow. Once the standpipe is already settled, we we stop the water flow and we allow water to go down from the standpipe. Okay, so from here, we can now solve for the area of the standpipe. Our K is given to be, sorry, our K is known to be 2.92 raised to negative 3. This is cms per seconds. That is equivalent to 2.303. The area of the standpipe is unknown by the length of the specimen, which is 38 centimeter, all over the area of the specimen, which is 19.4, this is cm square, by the time required for the water to draft from 64 cm to 30 cm is 8 minutes, or that is equivalent to 480 seconds. Okay, then we have, that is to be multiplied by log. Let me just write it here. Our h sub 1, or the head difference at time t equals 0, is 64 cm, and the head difference at time equals 8 minutes is 30 cm. So from here, the only unknown is A. There we can solve for the area of the standpipe, which is equivalent to 0.944 centimeter square. Okay, so that is the final answer.